Hi everyone, welcome to the NetAI session. It's great that there are people here, it's quite an early start. We have 6 exciting talks today, so we better start going through them. Our first talk is about MixNet, and it's a optical reconfigurable topology for mixture of experts models. And our speaker is Hudong. He's a PhD candidate in Hong Kong University of Science, and he's worked with Kai-Chen for this. So without further ado.
Thank you. Okay, sure. Okay, thank you for the introduction. This is Xudong from HKUST. Today I will be presenting our work on design interconnect for large-scale MOE training. This is a joint work with MIT, Peking University, Meta, in Badway, and Xiamen University. MOE models outperform has become a key scaling challenge in large language models. MOE model typically constrain multiple MOE blocks. For each MOE block, it contains one attention module, one gate unit, and several parallel neural networks called experts. Instead of activating all parameters from all experts, only a subset of them are selected for each token by the gating unit. This makes the training process more cost-efficient compared to the dense models. However, this computation sparsity also introduces communication challenges. Each token must be routed to different experts, and the result is dynamic and unpredictable communications patterns during the training, which is called computation-based routing. As models scale up, this computation cost grows non-linearly, and this quickly becomes the challenge of the communication. To plan MOE training in action, state-of-the-art training frameworks adopt multiple parallelisms. Among these, the most outstanding is expert parallelism. At each MOE layer, the token need to be shuffled across GPUs in an auto manner. The first auto dispatch tokens to selected experts, and the second one collect results from them. In addition, if a single expert is too large, we need to partition its model to a local subset of GPUs. This is called tensor partition, is TP. Together with other parallelisms include cross-stage pipeline parallelism and cross-model replica data parallelism. They form the whole training graph of the large-scale distributed MOE training across thousands of GPUs. To better understand the challenge, we first present a series of measurements on a production training cluster with advanced GPUs and high-speed networking. Together with optimized software, Nico and Megatron LM. We measure 3 representative MOE models. We found that first, the expert parallelism and the tensor parallelism contribute to the most communication-intensive dimensions. In addition, our timing results reveal that for each MOE layer, the auto communication consumes 35 to 55 of the training time. This is despite using the state-of-the-art cluster with high bandwidth InfiniBand networking and optimized NICO. The communication itself is still a challenge. Digging deeper, we found 3 important properties of the MOE traffic. First, the traffic is non-deterministic. The activation intensity of each expert varies significantly across the iterations. This means that the communication demands shift over time. Second, the traffic is non-uniform. In practice, heavy communication only occurs between a subset of GPUs, typically within the same MOE block. Moreover, this dynamic traffic range often regional. Here we plot the dynamic EP transfers within the 128 GPUs. We find that only experts within the same block communicate with each other. This is largely due to the pipeline parallelisms, in particular the PP in this setting. So this motivates us to design a new interconnect for the MOE training with the cost-efficient manner. On the one hand, electrical topologies such as factory or NVIDIA's reoptimized factory can provide enough bandwidth, but they are extremely costly. On the other hand, optical solutions such as TopOpt can reconfigure topology, but they operate at the job level with one-off reconfigurations, so they cannot keep up the runtime dynamics. So neither existing electrical or optical designs are a good fit. This motivate us to interconnect the cluster with a more cost-efficient manner. So, to answer this, we first conduct a first principle analysis based on the previous measurements. First, for each parallelism, we find that they have distinct properties and requirements on the lateral fabric. For example, for TP, its volume is most intensive, but it has the least scale because it's localized or reduced. Therefore, the commodity crossbar NV switch is a good fit. On the other hand, for EP, we find it's regional, it's non-deterministic, its bandwidth requirement is high, and we find it does not require the non-blocking factory, so we feel circuit switching, especially optical circuit switching, is a good fit. For DP and PP, the bandwidth requirement is low and their scope is large, so we feel Ethernet is a good fit. Given this analysis, the ideal fabric should, on the one hand, provide on-demand bandwidth where and when needed to balance the flexibility and the scalability. This comes to the design philosophy of MixNet that expands the NV switch fabric flexibly using optics while leveraging classical Ethernet for the scale. So this guides architecture of MixNet, a hybrid fabric of NV switch, Ethernet and optical circuit switching. The most inside each server, GPU are connected with NV switch. Between servers, GPU, some ports are connected in the global electric domain, while others are connected to a regional OCS domain. The core design of MixNet is the regional high bandwidth domain, which is reconfigurable with OCS. It provides regional flexibility. Instead of building a massive OCS, we partition the cluster into multiple regions, each equipped with its own OCS. With this architecture, from the application perspective, NV switch handles the logic-intensive TP, regional OCS handle EP, while global EPS handle PP and TP. Therefore, MixNet does not require a fully connectivity in the OCS domain. In this way, MixNet mitigates the trade-off between the OCS reconfiguration time and the switch port counts, making the runtime adaptation feasible. This allows us to reconfigure the topology for each high bandwidth domain regionally. In addition, this design mitigates the use of the long-range transceivers to mitigate the insertion loss for multiple circuit switching. OCS typically requires milliseconds to reconfigure, while we do not want to block the training process with that. So MixNet solves this by overlapping the reconfiguration with computation. We get the communication demand either from the collective primitives, such as the torch, the dist, the auto or single, or from some partial predictions. For example, during the forward parse, we can predict the upcoming auto patterns and reconfigure the topology in advance, so that by the time the communication begins, the fabric is ready. For the backward parse, the things is much simpler, because its demand is the same as that is in the forward parse, so we can just reconfigure the topology in a later layer of the attention computation. For the details of the reconfiguration algorithm and the prediction algorithms, please refer to our paper. So here is the system architecture of MixNet. As discussed earlier, we first get the traffic demand from the high-level primitives, such as torch, or auto, which does not incur extra overheads because every application requires these primitives to do the auto. Then we use this demand to reconfigure topologies. One thing to know that is in MixNet, we design the control plane in a fully decentralized manner, which means that each regional OCS has each regional controller. It avoids the centralized control plan for the whole fabric, so therefore it makes the OCS control scalable. In addition, we also design a customized collective communication for the MixNet's reconfigured topologies. We replace the PyTorch's default collective communication with MixNet's override version. Then we leverage NVLink and RDMA for the transmission. So this illustrates how the collective communications is performed within the reconfigured topologies. First, we have the traffic demands. Each OCS controller computed a topology with a heuristic gradient algorithm and enforce the topology by the reconfiguring the OCS fabric. After that, we need to figure out the routing policy of the direct connected topologies. So we need to figure out what is the gateway for each servers to communicate with each other. Then with this information, we can perform 3 stages of the collective communication in auto. Inside each machine, we first gathering the outbound data to each GPU's gateway. Then we leverage RDMA for the inter-host auto and leverage NV-switch NV-link for the intra-host auto. And finally, for each receivers, its gateway will dispatch the results to the final destination with the NV-switch. One thing to note that the medium to phase use different fabrics, so they can be overlapped to reduce the end-to-end communication time. So here is a concrete example of how MixNet operates. We take the red line of the example. It shows the EP transfer with indirect forwarding. First, one GPU in the server 0 want to talk with one GPU in the server 2. So it first to figure out the gateway GPU is the GPU 0. Then it first gather the outbound data to the GPU 0, then leverage RDMA to transfer the data from the 2 GPU 0s, and the final step is to dispatch the data from GPU 0 to the GPU 1, the final destination. This works similar for the blue line, which depicts the DP transfer. For the evaluations, we first build a prototype of MixNet to demonstrate the feasibility. We build a testbed contains several Ampere GPUs, several NICs, and one EPS switch and one OCS switch. We show the system is comparable of training the state-of-the-art models and achieve performance comparable to bandwidth equivalent EPS. We also did some large-scale simulations to evaluate MixNet at scale. The results show MixNet achieves comparable performance to 4 bisection bandwidth, long blocking factory, and re-optimized. We outperform other optical solutions significantly. We also do the Pareto analysis on the cost versus the performance. We find the MixNet always define the Pareto front among all the designs, makes MixNet a promising interconnect for the future large-scale AI clusters. Finally, we evaluate scalability. We find the system scale efficiently as the number of GPUs increase to up to 32,000 GPUs, demand the strong scalability. This shows that MixNet can meet the demand of next generation foundation model training. Looking forward, we envision MixNet to evolve to be a fully mixed fabric directly from the XPU computation device to cater to the further machine learning workloads. First, MixNet split the chip's I/O bandwidth to 3 parts. For the inner version, the internode MixNet provision the ultra-high bandwidth electrical interconnect, such as the NVL74. For the regional connect, MixNet leverages the co-packaged optics to enable medium-range, high-speed XPU direct optical interconnect. For the outer layer, MixNet enables the electrical Ethernet for the cluster ring scalability. We also did several evaluations, the simulation evaluations, to evaluate the co-packaged optics version of MixNet. For example, in the case of total bandwidth of the GPU is 8 terabytes per second, we grant 800 gigabytes to the scaled NICs and split the remaining bandwidth to NV-switch and regional optics. The results show that MixNet augments the existing hierarchics NVL system by up to 1.3 times. I want to conclude by recoupling MixNet is first of its kind system that design mixed optical-electrical fabric for large-scale distributed MOE training. It unlocks the runtime topology configurations. The core to MixNet is the design and the implementation of the regional reconfigurable high bandwidth domain, make it flexible yet scalable. We also know that the forwarding looking techniques like net matter passage, which is a scale-up optical interconnect, can benefit from MixNet by arranging reconfigurable OCS within the each group for providing massive optical bandwidth and intra-collective flexibility. Okay, thank you. That's all for my presentation. I'm happy to take questions.
Are there any questions?
Hi, thank you. Very nice talk. So from performance perspective, it seems that it's like a factory. So what is your most important selling point to sell that this architecture is better than electrical switching?
So you mean why MixNet is better than electrical switching?
Yeah, what is your most stronger point to convince me to go with this and not stay with electrical switches, because the performance, if I understood correct, is pretty similar.
Oh, yeah. The point is that we envision the MOE training does not require the long blocking, full bandwidth long blocking electrical fabric. So we're using optics to enable on-demand networking. Preserving the high performance while reducing the networking cost significantly. So MixNet is a more cost-efficient solution than the electrical factory.
Any other questions?
Hi, great talk. I'm just curious about, it is possible to expand the failure domain when you use the runtime reconfiguration. Yeah, and what, in your opinion, the possible solution? Okay.
So you mean why PaaS solutions cannot work in the regional design?
I mean the runtime reconfiguration. Is it possible to expand the failure domain during training?
Yes, we feel because the EP traffic is dynamic and non-uniform, therefore, for different iterations and different steps, the EP communication matrix is relatively very different. So we require the runtime topology configurations to adapt the topology to the runtime communication demands from the application. So that's the point of the runtime reconfiguration, because we need it to adapt to runtime demands.
Okay, thank you.
We have time for one more question if there are more takers. I wanted to ask, this is the third type of network that we have in these accelerators. So you've got the scale-up, the electrical scale-out, and the MixNet. So any chance we can get rid of one of these? It seems like 3 networks just for the GPU communication is a lot, because you also have the front-end network. So it seems like we're adding a lot of complexity. Do you think you can replace either the scale-up or the scale-out with something that's optical, maybe?
I think the point of MixNet is to blur the boundaries between the scale-up and the scale-out, because their bandwidth, the bandwidth difference is so large. The scale-up has too much ultra-high bandwidth. So we feel the optics can enable medium reach and high bandwidth compared to the scale-out optics. So I think it sets the boundary between scale-out and scale-up.
Thank you. Let's thank the speaker again.